sort of show you guys some kind of numerical tricks and then go over something that might be helpful on the project. So last time when we looked at this code, I went really fast over this part where I compute the tangent stiffness matrix. And I said this is a little trick I use to do it. So I was going to kind of show you in more detail what I'm doing there, okay? So if you if you have a function f of x and you do a Taylor series expansion where x is a complex number, if you do a Taylor series expansion about the point of f of I plus h plus about the point h equal to 0, then you get this guy. And so if we take the imaginary part of both sides of the equation and solve for the first derivative term, you get that. So an approximation of the first derivative of the function f of x is the imaginary part of f of x plus ih divided by h plus an error that's of order h squared. Okay? You ever seen that before? This is called a complex step method or complex Taylor series expansion. And it can be useful for approximating numerical derivatives. And if we compare it to, say, forward difference, or even central difference, right? So if you compare to forward difference, it's more accurate. Right? Forward difference has only one errors on of order h. Okay, so both of the complex step and the forward difference only require one perturbation of the function. In other words, you just have to perturb the function plus h, otherwise you just have the function, right? Which we're going to assume you're going to evaluate anyway, right? And so there's only one functional evaluation, but the complex step method is more accurate at the expense of complex numbers, right? You have to do this in a system that handles complex numbers well, okay? And of course, then the central difference method has the same order error, but now you have two perturbations, right? Two functional evaluations. So it's going to be twice as slow. Twice as slow as forward difference. Right? Turns out, and Michael wrote a whole paper on this, in implementing these to compute tangent stiffness matrices in a massively parallel code. It turns out that because you're using complex numbers, which are slower than reals, that the speed of the complex step method and the central difference method about the same. So this is twice as slow as that, roughly, and it's about the same as that. Right? But the real advantage comes in, of course, if we're going to use this for Newton iterations, we want very accurate tangents so that we get quadratic convergence. And so this is only accurate when this is small, when h is small. But if it's too small, then you get subtractive cancellation because you're subtracting two numbers that are really close to one another, right? So if this is like, in practice, it's rare that you can make this guy in a central difference scheme smaller than like 10 to the minus 6 or 7th or something like that. Because if it's too small, then you're basically subtracting a number minus a number that's very close to it, and you get 0.0000000000, and there's error out there. So the complex step method has the advantage in that you can make h as small as you want. And in fact, I've often made it, I think in the example that I showed, it's like e to the minus 50. You can make it e to the minus 100, it doesn't matter. And you'll get very, very accurate derivative, okay? Again, at the at the expense of having to use complex numbers. But if you're writing your code in MATLAB or Mathematica or even Python, some interpreted language, code's slow already. In that case, and those actually have decent complex number implementations. So also the ease in which you can program it is a little bit nicer. So and there's no sort of heuristics in how you choose h. And if you use one of these methods, there's going to be some heuristic in how you choose h. Up there, you just don't think about it. Make h tiny, e to the minus 50, 1 e to the minus 50, and you get a very accurate derivative. So to show you a simple example, so imagine we have a function that takes in a vector x, y, z, and returns some function of that, right? So I'm just making this up, but y squared y plus z cubed. So let's look at what the analytic gradient of that is, right? Or the analytic, if this is imagine this is our total force calculation. Some vector goes in, and the force is what comes out, right, on the other side. So then the tangent stiffness would be the derivative with respect to x of the whole thing, right? The derivative with respect to y with the whole thing. That would be the first column, second column. The derivative with respect to z of the whole thing, third column, right? So we can just, since this is mathematical, we can do that in closed form, right? We can just say like, all right, we're going to create a table where f is a function of x1, x2, x3. So those are the inputs to our vector. And then we're going to take the derivative with respect to xi, all right? And then we're going to stick that in a table where I goes from 1 to 3. I forgot my parentheses here. I mean my brackets. Right, there we go. So everybody can see that. You can read it off, right? I mean, take the derivative of the, so the first I take the derivative with respect to x, and I get 1, 1, 0. Right? That's the first three. Derivative with respect to y, I get 0, 2y, 1. Right? In this case, 2, x2, whatever, right? Because I plugged in x2 for y. Right? But ultimately, we're doing this because we're doing it numerically, right? So let's, for sake of comparison, what we'll do next, let's just set x1 equal to 1, x2 equal to 2, x3 equal to 3. All right, so there's our tangent stiffness, or the transpose of it, but it doesn't really matter. Because the way that came out, it was row by row. I'd have to actually transpose it to be consistent with what I said, but that doesn't really matter for what we're arguing here, right? So then what I'm saying is, okay, I can take f of 1, 2, 3, right? Because that's what I evaluated x1, x2, and x3 at, right? I can take f of 1, 2, 3, and I can perturb it by IH, right? There I get a function, and if I take the imaginary part of that guy, divide by h, take the imaginary part, then I think I can simplify it with the assumption that h is greater than 0. IH 0, 0. There we go. Right, so I perturb, so that's just the first column. Right? I perturb the first one. And I could do the second and third individually, right? So if I just change this from 0 to IH here, I get that, the second column. Right? So then I can use a trick, right? So I have this, mathematics is a functional language, so I can basically make this whole expression a pure function, and I do that by putting that there and that there, and that's just syntax, and you see it turn green. So now this thing is a pure function in which I can map an array. I can call this function on an array, where my array would be values that I'm going to perturb that get substituted in where that pound sign is. And so the array that I need to, the shorthand notation to map is this guy, and the array that I need to map is just the identity matrix. That's a 3 by 3 times IH. Now remember I said it has order error h squared, so that's what this guy is. But how small can we make h? So I can substitute in h 1 times 10 e to the minus 50. And I get the same answer. Right? So the one on top is analytic, right? It's exact. And using my complex step method for numerical derivative, I get something that's very, very close.
Is it perturbing if you do that at the same time?
No. So it's a little bit, you have to sort of know a little bit about functional language. So the identity matrix is 1, 0, 0, or I multiplied it by IH, so it's really IH 0, 0, right? So what that map function does is it takes the first row and it replaces it right there, right? and then it takes the second row and does the same thing, and then the third row and does the same thing, and it creates a two-dimensional thing that comes out. So it's actually really pretty slick, compact.
If you were using multi-complex numbers, you could probably perturb all three at once. I think that's
Yeah.
what Dr. Millwater was doing.
Well, usually you use multi-complex numbers are where the multi-complex numbers, your h would be also a complex number. And using multi-complex numbers, you can get higher order derivatives. So you can get second derivatives, and you can go on up, right? So because you're going to perturb, your h is going to be a complex number with another perturbation, IH, in it, and then you can continue to do that, right? And so there's a little bit, to try to work it out in a way like this, it's a little bit tricky. The way there's some matrix methods that correspond to it, and yeah, you can do it like that. But again, if you're using a real language, when I say real language, there's only one, C++. If you're using a real language, you just use an automatic differentiation library. And you can even get second derivatives from that, or third or 100th. Although the coding for 100th derivative would not be nice, but I think. Because you'd have to template the template 100 times. Anyway, yeah. The best way is, of course, automatic differentiation. But if you're using I say the best way. It's not always the best to go and use C++ for a very simple problem, right? Unless you're just a real expert and you can get it done faster that way. I think it's doubtful in most sort of problems we solve in class that it's beneficial to do that. So, and if you're just going to use, MATLAB or Mathematica or Python or something, this is a nice little trick for computing derivatives. Actually, and here we use it for tangent stemness, but I've used it in optimization schemes and all kinds of stuff. I mean, anywhere you need a numerical derivative, it works really well. So, back to this guy. Okay, so look at the compute force, okay? It takes in the deformed position, and then there's I say partition. That just means take my one-dimensional array and partition it into pairs, resize it, if you will. Probably in MATLAB, the command's like resize or something like that. So take my one-dimensional array that's coming in as a perturbation and resize it into a two-dimensional array that have components x and y. Because the displacement or the deformed position has that, the coordinates have x and y, okay? Now, and then you see my little hash mark, right? So, and all the rest of that's just material properties and old stresses coming, because we're updating, it's an incremental formulation, we're updating the stresses, okay? But then you see my ampersand on the end. That makes that whole compute force thing a pure function that I'm then going to map the identity matrix that is the size 2 times the length of nodes, because each node has 2 degrees of freedom, right? So my identity matrix is 2 times the length of nodes times IH, right? And because I'm using an updated Lagrangian scheme, my deformed position comes in every time. It's updated. So I'm perturbing around the deformed position, which is the reference position, which is essentially the displacements are the zero vector at that time. That's why you don't see something plus partition, whatever, right? Like here, I had to say 1, 2, 3 plus hash mark, because I'm linearizing. In that case, I was linearizing about the point 1, 2, 3. Okay. Here, I'm linearizing about the zero displacement vector, because I've updated my deformed position every time, which is my reference position. Every time I update it, it's the same thing as saying there's no displacement, right? All right, so I perturb the whole thing, and then what comes out, I just transpose it, take the imaginary part of it, and divide by h, and then I get the tangent stiffness. So pretty nice one-liner, right? I mean, even a forward difference scheme, you'd have to evaluate the function at the zero vector, evaluate the function at a perturbation of that. So, it definitely there's no way to do it in one line like that. Although it is kind of a long line. Oh, just the last thing is that map. So on my simple example, I used the shorthand there. I could have just the same said map. So that little slash at is just shorthand for map, right? So the syntax there is, the function you're going to evaluate and then what you're mapping over it, comma. So map, the function you're going to evaluate, what you're going to map over it, comma, what you're going to map over it. All right? Is that interesting to anyone?